So my name is Brian Kaufman. I'm with the software engineering group that puts this model together and releases it. Yeah, this talk is about the source code and the scripts that it takes to run it and the general process of running it. And the slides are pretty dense, so it's not a normal PowerPoint, I guess, just hitting the high points. I tried to put a lot of information in it, so they are pretty dense, but some people will want that information or may want it later. But initially, what you need to try to do is pick out the highlights and kind of keep your eye on the high-level picture of things and not let the details confuse you too much. So what we're up to is we have a climate model, CCSM 4, the Community Climate System Model version 4, that we released a few months ago, and then the follow-on version, which we've christened CESM, Community Earth System Model version 1, that we're going to release tomorrow. And this is what I'm going to cover. Okay, so just a little bit about what this model is all about, point you to our release homepage, talk a little bit about software and hardware requirements, and then basically give you a feel for the basic workflow. And that would include some one-time setups, acquiring the code and getting it ported to your machine. And then something that you would do over and over again if you're using the code is to create a case, to create a simulation, run that simulation, and then you would repeat that process to do other simulations. Okay, so first of all, what is CESM? It's a Community Earth System Model and was Community Climate System Model. It's a global climate model. It's used to do simulations like those that would be, maybe global warming simulations or paleoclimate simulations. We played a pretty big role in the last IPCC report. CCSM 4 that we released a few months ago had 4 components. So basically the way this game is played is you have an atmosphere component, a land component, an ocean component, an ice component, and the software is connected together by a coupler component. And then with our new releases, we've added a land glacier component. And this diagram's showing we have these components that all connect to this coupler software, and the coupler controls the interaction between the different players. And so the atmosphere, for example, is a component, and the component's a basic concept in our software. You have an atmosphere component. You can swap it in for an alternate atmosphere component. And this concept shows up elsewhere. On our input data sets are categorized by what component are they for. Our output data sets are categorized by what component are they for. The software is broken down into this directory has all the software for a certain component. First place to go for any information about this is we have release home pages. A little bit about software and hardware requirements. You can't.
That one is CSM1.
Yeah. Okay. So the URL here is www.cesm.ucar.edu/models/CESM1.0. Just to hit a few items about software and hardware, we require this Subversion software, which is free. It's a software control software, and you have to interact through Subversion to pull out the source code you want, and we also use it to get at the input data files you need. So you request things by way of this Subversion software. you'll need Fortran and C compilers. That's pretty standard. A netcdf library, so the input and output data is generally all in this netcdf format, some self-describing format. So you need a netcdf library available, MPI library, which is pretty standard on supercomputers and similar. As far as hardware, I can't really describe fully what you need for hardware, but here's a list of machines that we've ported to. And so roughly maybe hardware like this. Certain very simple configurations you can actually run on a laptop, but that might be like a one-point model. Generally, bigger machines like these listed here, IBM's Crays, SGI Linux clusters. Okay, so the basic workflow of using this model is there's some one-time setups that you need to do, namely getting the source code, setting up a location for your input data, your initial condition files. You may have to port, if it's ported to several machines, but you may have to port to a different machine. And then there's, for each experiment, you go through this process of creating and running a case. And I'll be walking through that. Okay, so to get the software, it's freely available to anybody, but you need to go to our website and you need to register for it. And you'll be emailed a username and password. And then you can use the Subversion software to download the code. If you don't have it, you can get it for free at this website. It's pretty straightforward to use. Basically, once you get it installed, you can say SVN, check me out, this software, and you give it a URL. That's the root level of our software. And I guess what this is showing here is, your screen will, all these files will start scrolling across your screen. It's downloading the code. And this is what you get when you download the code. There's a whole directory structure. It's right away at the top level, it's split into two pieces. There's all the model source code, and then there's scripts that are used to run that code, to build and run it. And in the model source code, it's categorized by component. So there we see, our atmosphere component, land component, ocean, ice, glacier, and the driver coupler component. And then for each component, there's generally several choices. There's an active atmosphere model, the CAM model, of which WAACM is part of. But there's an alternate atmosphere model. We call it a data model. It interacts with the system as if it were an atmosphere, but it's just reading usually observational data off a input file and feeding it to the coupler, presenting itself as an atmosphere. Okay, so that was getting the source code and roughly what you get. And then another one-time setup is you need to create a directory where all your input initial condition data will reside. If you're on a machine that we've already ported to, this directory already exists and there's nothing to do. If you're porting to a new machine, you'll need to create an area where your input data exists. If a variety of people are going to be running this model, you should coordinate with these other people and create one area, one shared area to put in your initial condition files, because they can be quite large, and you don't want to have duplicate copies of everything, so you would create a shared area. If you do need to create your own input data area, you don't want to download the data like the source code, all right? We have a method later, a script that will grab just the data you need for the simulations you want to do. If you try to grab all the data, it's probably a terabyte of data. you don't want to just download it all. You just want to grab the subset that you need. There's scripts to do that. Okay, so what do we have? This is a picture of the directories at play when you use this model. This is the directory you got when you downloaded the source code, and I just mentioned that you want to create an area for input data to be. So as the slides move on, this page will get filled out with more directories of things that are at play when you run this model. Okay, so the next step would be porting. And basically, porting is beyond the scope of this talk. All right, it can be quite involved. First of all, if you have access to a supported machine, there's nothing to do. You don't have to port. It's already been ported. But if you're going to port the code to a new machine, it could be relatively easy and it could be quite difficult. It's pretty open-ended what kind of hardware you might have. So if you do need to get into that, we have documentation on the web that you should look at. And that's all I'm going to say about that. Except, again, it could be quite easy if it's similar to a machine that we've already ported to, that we support. And really, it all depends on what exactly you're trying to port it to.
If you're running on a machine that you have run on before, does it automatically detect like the MPI header files and which make file to use and which command to use with the configuration script?
So when you download the code, there's files that have all the information to run on a given machine. A machine by name. So if you're running on that machine, in a few slides you'll say I want to run a case and I want to run it on this machine, and if it's a machine it understands, you're golden. It knows all the details.
But the probability of that is quite low. I mean, so if you have MPI headers somewhere and a make file, you're using Portland Group Compiler, you're using MPI
Yeah, so we have a strategy for this. I can't really get into it because it gets kind of detailed, but we have like what we call generic machines. We have all the information for a generic Linux cluster. And we've taken pretty darn good guesses of what all the settings ought to be, and there might be just a handful that we don't know where your compiler is located, what directory or something. And it gets you a long way there, and there's a few blanks to fill in for that machine.
Like a script or something like that, or is it like a config file or something like that you modify? Or
There'll be a handful of files, maybe 3, that have all the details about a particular machine. And say you have a Linux cluster, but it's unsupported. You pull the files for a generic Linux cluster, and you look through them. They're not that long, and there's a few spots it'll point out that say, you need to fill in this blank. Where's this library or something, or where's your input data? Where did you put it? So there's a handful of blanks you need to fill in, and some pretty good guesses about all the other settings. But you need to kind of look through them and see, okay, what's different about the machine I have.
And the name of those files that you have to modify are like highlighted in the README file or something like that?
Yeah.
Okay.
Take a look at the user's guide. There's a section on it, and it points these things out. All right, so you can actually, so suppose we're on a machine where it's already been ported to. You can actually run the model with maybe 6 or 7 command line type in and hit return, right? And here's an example. I could take this to my machine and just submit it as a shell script, and it would run. And half of these commands aren't really even needed. They're like listing of directories where I'm poking around to see, what kind of output I got. So if you run out of the box, we have this notion, out of the box. You didn't change anything. You just create it, use all the default settings. You could, on a ported machine, you could run the model in maybe 6 command line arguments. But of course, there's a lot of detail. But the point here is like as a new user, try to stay focused on a few things you really need to do, and I'll give you a feel for all the details of things that you might change and what's going on around that. But just try to do the simplest thing out of the box first, and then start tweaking things and getting the run you really want. Okay, so now we're going to get into the flow when you create a particular case to run a particular simulation. The first thing you need to do is you go into that source code download, and you go into the scripts directory, and in there is a script that has the name create new case, which is highlighted there. Okay, we want to run this script. It has a -help option where you can see all the arguments that go along with that script, but you really don't need to know most of them. There are 4 that are required, and I'm going to talk about those. Okay, so here's an example of executing that script, and it's 4 arguments. The first argument there is a case. You're going to run a simulation. You want to give it a name. In this case, my case 1. All right? And what's going to happen, and you give it a directory location. So when you run this, it's going to create a directory called my case in the place you told it to, and it's going to populate that directory with the scripts that you need to run that case. Also, at this point of the game, you need to pick what's the resolution of the model I want to run. So this is saying F19G16. What this is saying is the atmosphere resolution is a nominal 1.9 degree grid, and then the ocean resolution is a nominal 1 degree grid. These are, I'll talk about what the options are in just a minute, but you're picking the resolution of the model, coarse, fine. You pick a comp set. So a comp set, so I was saying we have different components, like an atmosphere component and an ocean component. Well, you have choices for the atmosphere component. Do you have the actual active CAM model, or do you have this data model component? And similar for the other components, ocean, ice, land. Different sets of components are assigned a letter name, like B is all the active components, no data models. F is data ocean, active other models. Okay, a bit more about that on the next slide, but you pick your case, you pick your resolution, you pick your comp set, and then finally you pick your machine, right? So in this case, there's a machine called Bluefire. The scripts know Bluefire. There's a few files that are all the details about Bluefire. Where's the input data? What's the compiler? What's the batch job run script? It's those few files that you would have to modify if you're porting to a new machine. Okay, you can run this create new case with a -list option, and it'll tell you all your valid choices for the things I just mentioned. So here there's, at the top there's a bunch of resolution choices, then followed by a bunch of comp set choices. So here's where it tells you that a B comp set is all active models, or an F is data ocean. And then finally at the bottom there's a bunch of machines that you can choose from. Actually, there's a lot more choices in this. I've pared down the list to fit it on one slide. But the point is, you can do this -list and see all the valid options that are already built into the model. You can add some if you get into porting, like you could add an option for another machine. And here I'm just pulling out a couple, well, the WAACM comp set options that are built in. So there's 3 B comp sets. That's all active models. I guess what's happening here is B 1850 is like a constant 1850 forcing. So it's kind of like a pre-industrial spin-up run. And then this B 1850 to 2000, that sets up a run that simulates the 20th century. We use this to validate our models to see if they reasonably replicate the 20th century as a hindcast. The F comp set's similar, but without an active ocean model, with a data ocean model.
So if you were interested in looking at like waves propagating up and what the effect is on the thermosphere, and that's all you really cared about, what one would you pick?
Yeah, 2000.
Sorry?
Probably an S2000.
Yeah, can you go back? The last case is sort of a perpetual 2000 with a mean climatological sea surface temperature. So that's what I would recommend everyone start out running if they're going to try and run WAACM, because it's sort of a perpetual run for a fixed.
The bottom one.
Yes, that's the easiest one to get going.
Right, so the bottom case, the F2000 WAACM, good place to start. So the 2000 is constant present day conditions, roughly as forcing conditions.
And by forcing conditions, you're basically saying
Carbon dioxide
carbon dioxide,
and
sea surface temperatures, and ice coverage. Okay.
When do you use the variable in your parentheses? What's the...
Oh, yeah, what's going on there, a detail I didn't point out on the last slide, it's a equivalent short name for the longer name. So when you pick a comp set, you can pick the long name on the left or the shorter name in parentheses. When you get to be a power user, you want like shorthand for everything. So, okay, so here's what you would see on your screen if you actually ran this command, create new case. The first thing you're going to do to set up your simulation. So what's happening here is the first thing you get is a warning. So we've scientifically validated certain configurations of this model. We believe they result in good science. But there's a lot of other configurations you can use, and we don't know what they do. They probably work well, but we haven't done the simulations and examined them. So you just need to be aware, are you running a configuration that we've looked into and validated, or are you doing some other simulation? This list is actually for the CCSM4 release that was a few months ago. The list of validated configurations for the release tomorrow is considerably longer and includes WAACM runs. Anyway, it's just warning you that there's a subset of things you can do that have been scientifically validated. And then it's mentioning down here that it's creating this directory where you told it to with the -case option, and hopefully there'll be a thing down here that says it was successful in running this command.
What are common ways that you can screw up there?
I don't know. I mean, if you pick an invalid...
For the case of WAACM, we've restricted it that only the scientifically valid combinations are actually allowed. So you can't really screw up there. You're only going to get a working mode.
Okay.
So it's not, so if you were to pick, you can't get these whatever possible permutations of all the different components. When you run WAACM, you only get a few options.
What's going to happen, the most likely scenario of screwing up is you'll pick some invalid option, and the script will come back and say, that's an invalid option. You know, put the listing and say, pick from this list.
Yeah. Okay.
So, well, it's a climate model. I mean, there's a lot of ways you could screw it up, but if you run out of the box and you pick from the valid set of things.
Only a really smart idiot could.
I don't know. This isn't rocket science, but it's not. I don't know. Might be close. I don't know. Okay, so here to add the directories at play, we downloaded the code. We made an input data directory. We ran this create new case, and it created a directory somewhere, wherever you told it. And often, it'll be in a different location than where the source code is. Like maybe the source code is in some shared directory where you and your colleagues can all access the same code, but your case, you made it in your home directory where they can't muck with it. Anyway, create new case made a directory for you where you told it to, and here's an actual listing of what shows up in there. So let's take a quick look at the stuff in there. Okay, so to point out a few things, there's a directory into which you can put modified versions of source code. It's initially, there's nothing in it. It's going to run the out-of-the-box default source code, but later you might modify some file and throw it in there, and then your run will pick that up and behave differently depending on what you did to the source code. There's this configure script, which is the second command we're going to need in the shortest possible process of running this code. There's a bunch of files that start with env and end and .xml, and I'm going to talk about them in just a second, and a script at the bottom called XML change. So what's happening with these files that start with env and end and .xml is they're XML files, and in them are variables that come with nice default values, but you can change them to alter how the run, what your simulation is, all right? So initially you want to start out of the box, just use these recommended values for everything and just do an out of the box run. And later, when you get comfortable, you can start thinking about changing variables to get a new simulation that you're interested in. So here's just a little bit more about that, like what's the format of these. It might take just a little bit to get used to, but basically there's lines in there that say there's a variable and it has this name and it has this value, and it might have a list of acceptable values, and then it'll have there's something in there that says, and it's a character string, or it's an integer, or it's a real number. So you can poke around in there, and it won't take too long. You'll get a feel for how to, identify a variable and its value. That on the last slide I mentioned there was this script called XML change, and you can use that to change the value of an XML variable. And it's useful to use this. Actually, you can just go in there with an editor, Emacs or VI or something, and change the value. But if you use this script, it's safer because it won't make typos, and it'll check, this variable is supposed to be a character string, and it has these valid values. It'll check and reduce the chance of you picking an invalid value or screwing up the format of the XML file.
This is like where you set what day you want to start on, what day you want to end on,
yeah, one of the,
how often you want files output.
Right, so one of these files is, I want to do a 5-month simulation. No, wait, I want to do a 5-year simulation. You pick things like this. And there's another tool that usually you don't have to use, but I'm going to point it out. So the XML files are really handy for managing information like this. But when the scripts actually run, they need this information as Unix environment variables. So at some point, the scripts behind this under the covers need to change these XML values into environment variables. But you can do that yourself with your own Unix environment variables by doing this command at the bottom here. And you can use this to see the final value of certain variables, which is handy in a handful of cases. Okay, so here's these XML files kind of grouped together. They're about different things. So the first one at the top actually was created when we ran that create new case command. And actually you can't change it. It's just keeping track of the choices that you made when you ran that create new case. So you can look at it as a record of what choices you made, but you can't change it. You're locked into that. So I have this notion of being locked into choices. So after you run create new case, you're locked into the XML choices. The next step's going to be this command called configure, and there's an associated XML file, env conf.xml that you can edit before you run configure but not after, and you can pick things like, what's the first year of my simulation? Is it year 1? Is it year 1850? Is it year 1980? You can make choices like this. But at a certain point, you're locked in, and the model won't let you change that.
In most, I don't know about the rest of the people, but there, in the ionosphere-thermosphere stuff, we run for like a week, and that's all we run for. But with WAACM, it sounds like you don't ever run for a week. You run for a year, or 2 years, or 3 years. Is that true? And so we're not dealing with like...
I'm going to pass it over to the...
No.
Yeah, I mean,
So you can run for, like, if we want to run like an
on the
event.
previous page, it said that your timing was n days. You had a stop date, or so you said you can put in
Does it-
7.
Does it like restart from some nominal condition and then continue from there? Or
Yeah.
do you cold start it and it takes a while to spin up? So you have to be careful about how long you run before you really want to look at the solutions, or?
Right, but then you can branch and do an ensemble of
Yeah.
7-day simulations where you're picking one little parameter, change your KP
Yeah, yeah.
or something. So it's very flexible.
Okay.
There-
You're not locked into decadal configurations.
One thing that happens automatically is, like, certain comp sets have associated initial conditions. Well, they all have associated initial conditions, but some of them are spun up, right? So if you haven't made significant code changes, the initial conditions should be a pretty smooth fit, and maybe no spin up is necessary. Or hypothetically, you could make radical changes to the source code, and you'll have to spin it up for 20 years or 100 years or whatever, depending what you did. Anyway, env conf is the variables you have to choose before you configure, and here's some examples of the variables in there. Is it year 1, 1850?
So these XML files are like the old name lists, where you can change that?
No, they're not like the name list, but they're used in constructing the name list. The name list still exists, but this information is used in constructing those name lists.
Are these the only files that you have to change a case?
Not necessarily. This is sort of a higher level choice you can make, and if you change some value in there, it's possible that 10 nameless variables will change as a result of this sort of higher level choice. And then further downstream, you could go and tweak just one of those 10. So it's a higher level thing than nameless. A choice here may impact a bunch of nameless variables, which later you could individually tweak.
But are those other things in the other files, or?
Yes. So what happens here is you make high-level choices that narrow down the set of subsequent choices. And then so when you created a new case, right, you picked a resolution and a comp set. That ruled out a lot of things. But it didn't rule out everything, but it kind of narrowed the scope of remaining choices. And this one will further narrow the set of remaining choices, but there are more. Okay, so this next batch has to do with building and running the code. This env mock PEs, env machine PEs. In here, again, it has good default values. You probably don't want to play with it right away, but what you can do here is pick the number of processors that your job will run on. That's not uncommon. env build has information like maybe where certain libraries are. You probably don't want to change that, but it's in there. This macros file isn't really an XML file, but it's kind of similar to the two above that has to do with building. Like it might have compiler options in it. Okay, generally you probably don't want to change them, but you could if you know what you're doing. But initially you won't want to fool with that. The last one is the one you're most likely to change, in fact, almost certain to change, and that you can change it at any point because it it has things like, how long do I want to run? 5 days, 5 months, 5 years? And you can change that anywhere. You know, if you're doing a 100-year simulation, you could start out running a day at a time, then switch to a week, and a month, and a year. You know, anywhere along the line. Anytime you resubmit and continue the simulation, you can. There's choices you can make, and you can make them in there.
Can you, if you decide to run on 64 processors and you want to restart, can you restart on 128 processors, or are you locked in then for your entire run on 64 processors?
You're going to need to rebuild. You're not locked in. There's a way to change it.
So when you compile the code, you basically tell it how many processors you're going to run on?
Yes.
Wow. Okay.
The different components have different constraints about whether they need to be recompiled. Yes?
So when Dan was mentioning the app conf set, that conf set does not matter in terms of rebuilding and running on different PEs, because you're running CAM, which is independent of PEs, doesn't need to be rebuilt. But some of the other components do care, because they actually have parameters that are dependent on the number of PEs you're using in the block site. But
Yeah, yeah.
for the app, that's not an issue. You do have to issue a rebuild command to get the scripts to be smart enough to realize that a different PE layout was chosen, but it does nothing. It just goes through and just takes 2 seconds, and then you're ready to run.
Yeah, there's two issues. Like a code might need to be recompiled on account of a different number of processor count. I'm not even sure if that's true anymore.
It is for the IC notion.
Oh, okay. And then the other thing is the scripts need to understand how many processors am I supposed to be running on, and how many do the atmosphere have, and how many do the ocean have. And you can change these things, but you kind of need to like back up a step and change the value and step forward and have the system kind of ingest all this information. So at some point we'll build the code in a few slides. And after you build, then the number of PEs becomes locked. Actually, there's a way to unlock everything. I don't have time to get into that, but yeah. Oh, and here's an example then of this PE file. You know, you can say, okay, the atmosphere is going to run on, can't read it up there, 64 PEs, and it's unthreaded. It's 1 thread per PE, you know, and et cetera. And you can play with these things and try to get your job to run more efficiently or more quickly, depending on how many processors you have available. Okay, so what happened? We ran this create new case, and we looked at all the files that it created in your case directory. And I pointed out that there's a script in there called configure, and that's the next step to run that. There it is. So here's the case directory. Like, hypothetically, this is in my home directory, cases subdirectory. I want to run this configure command. The 2 XML files pointed out are the 2 that are going to become locked when you run this configure command. Configure has a help to it. Not much you need to know about that, but here's what you do. You just configure -case. It takes information from those 2 XML files, right, that I pointed out there, uses them. It's going to create more scripts for you. It's going to lock down some choices and narrow the scope of things that can be changed. You're kind of zeroing in on the exact simulation you're going to get. There's some comments there. It's saying it's generating a build script and a run script. That's what you're going to use to actually compile the code, and the run script you submit to the batch queue. And it's making some other scripts and files that I'm going to go through in just a minute. Okay, so the red arrow is pointing out what did we just add by running this configure script. It created a directory called build conf, comps for configure, so build configure, some information about building and configuring the code. it made a script that can build an executable, a script that you submit to the batch job, and a bunch of files in here, which I'm going to go over. So a new subdirectory with a bunch of files in them. In your case directory, okay, so there's the new scripts, the build and run, and a few more that I won't get into, and this new subdirectory here, which I'm going to drill down into. What's in there? Here we have, let's just apologize for the small type, but if you really get into this, you'll appreciate the detail if you follow these slides. So here for the CAM model, the first thing is, I can't read it up there, build exe, right? So that's gonna compile the CAM code. That's the script that does it. Below it is build NML. That's the script that's going to build the nameless file that CAM's going to read. And then the third one there is the CAM input data list. This is interesting and important. This is a list of all the input files that CAM's going to need. And for all the other components, the ice model, the land, the ocean, similar things. A script that will compile the code, a script that will build its name list, and a file that lists all the input data files that it needs.
So which one is WAACM?
WAACM is CAM. WAACM is a capability of CAM. Okay, so where are we at? We ran create new case, we did this configure thing, and we're about to build the code. That's where we are in the code flow. Okay, so you're going to do it by just running on the command line this build script. The build script's going to lock some of those env XML files, the ones having to do with building that were a few slides back. The way this works is that each individual component gets compiled into a library, and then we link all the libraries together and we get one executable to run. Now the other thing that the build, so the build does a few things. So it makes the libraries an executable. It runs this build nameless script. So it generates the nameless files for all the models. And then finally, it looks at those lists of files that all the components needed to get off the ground, all the input files. And it checks to see if they're in your input data directory. And if they're not, the build's going to abort, and it's going to say, I'm aborting because you don't have all the input data you need. You need to go get it. And the way you go get it is there's this, I've got to find it here. There's this, to come out here, check input data minus export. What this does, so suppose you're missing data, the build aborts, it says you're missing data. You got to run this command here. And what this command here is going to do is it's going to look at all the files that you need that you don't have, and it's going to, under the covers, use SVN to grab just those files and populate your input data. And this is the way to go because it knows exactly what you need. It's not going to get more than you need, and it knows where to put them because this input data has subdirectories and sub-subdirectories, and it knows where everything belongs, and it'll get it in there for you.
Do you have to set environment variables to do that, or is it already set up and so it reads files?
All you need to do is tell it where the root level of your input data is. And again, if you're on a supported machine, you don't need to do anything. But if you're porting to a new machine, you just pick the root level of where you want your input data, and this will populate it and make all the subdirectories and get everything in the right place and not get more than the minimum you need to run your simulation. Okay, so we want to run this build script. Where is it? This is the case directory. So there's the build script. Here's the env build that you could edit before building but not after. And here's this script that you will run if you need to get some input data. Well, now the other thing you might want to do before you build is you might want to modify source code. Well, first go around, don't modify source code. Just run it out of the box. Don't change anything, okay? But that'll get old, and then you'll want to change some source code. And there's two choices, and generally of where to do it, and generally one's a really good choice and one's a pretty bad choice. So in the case directory here, there's a subdirectory where you can put in modified source code. Initially, there's nothing in it, but you can, and then over here is the code that was downloaded by you or somebody. It's the base unmodified code that was downloaded. You can grab a file from here, throw it into your source mods directory, change something about it. You know, change the value of gravity or something, I don't know. And when you build, it'll pick up this code, it'll override this code, and you'll run a different simulation with that modification. Now you could change it here, but this is very dangerous and generally a bad idea, because every case you make will pick up this change. And if you have a colleague who's also making cases, they're going to pick up that change. And more often than not, if you make a change over here, someone's going to pick it up and they won't know it, and they're going to get a simulation that is wrong and they don't know it. So generally, don't make changes here, make it over here.
So probably too detailed question, but when you do a build, does it like copy all these files somewhere else and then copy the source mods and overwrite those and then build it? And then
No, what it does is it looks...
we can talk about that.
I think there's a path. Well, it has paths of where to look for source code, and if this path is before that one and has priority over that one, and this is the first in the path. So it'll, if it's here and here, that wins.
Makes sense.
Okay, so here's what your screen looks like if you actually run build. Let's see what we got going on here. There's some comments about checking that your data is actually there. Here's where it would terminate if you were missing something. Then it builds the different components one at a time. It puts the results in a library that eventually get linked together into one executable, and then hopefully at the end you'll see success. And here's what happens in the directory structure world. We had all this stuff. We ran build, and so the arrow up here is about, it's checking, do you have all the input data you need? This business here is, there's a place where the code's going to be, where it's going to compile and run. And it's generally going to be different than here and there. It's going to create directories for all the components. It's going to build the libraries in all these directories here. Then it's going to link all these libraries together and put an executable in here. And where is here? If you don't know where it is, a few slides back I was saying you can turn XML variables into environment variables. And if you do that, and you look at the value of this environment variable, that's where this all, well, that's where this directory is, and these are sibling directories in a parent directory. Or you can get the value of this. Yeah, so you can find out where this got all compiled and where your executable is. Okay, so that's what's happening here. You know, so I ran that, I got the value of this, and I did a listing on it, and you know, you built it. I don't know. I like to see, show me an executable. Where, you know, you said success, but you look in here, and sure enough, there's the executable. It's the big file, and then these build log files have the output from the build process. You know, hypothetically, there might be a compile error in there if it wasn't successful, or some warnings about source code syntax or something. And then this ATM-N, that's a nameless file. There's more nameless files here, right? So the build made the nameless files. They're in there. Made the executable. It's in there. And it checked that you had all the input data you need. Okay, so we created a case. We configured it, which narrowed down exactly what the case was going to do. We built the executable, and the next step, we're actually going to run this thing. And I broke it down into two. There's an initial run and a continuation run. So an initial run, you know, it's cold start. You want to do a short run. You want to poke around and see that it seems to be working correctly and doing what you expected it to do. And you want to spend a little quality time on step 4 and see that things look good before you go and start continuing this and doing a 100-year simulation. Okay, so I'm going to go back. The slide we saw before, but this was, you know, I claimed, and I still claim that, you know, with 6 or 10 command lines and returns, you can actually run this model. And where are we in this process? So we went into, we created a new case there in the source code directory, and then we CD'd over to where I created my case. We ran configure, we ran build. I did a listing on the run directory to see what was in there. And here's step 4. I would actually submit a job. Exactly how you submit it is machine dependent. I mean, generally you're going to be running in a batch queue. Maybe somebody somewhere has their own machine and they don't have to run in a batch queue, but most people do. So this is what we're up to next, actually running this code. Okay, so out of the box, this initial run is going to be a 5-day run. That's a pretty good idea. But you could change that if you wanted to by editing this env run XML file. Also, before you run, I mean, another thing you could do, like we talked about before, you could selectively edit certain nameless variables. And the way you would do that is you'd go into this build conf directory and edit the script. You know, if there's like a cam.build nameless, if you want to change cam nameless variables, you go in here and that'll edit cam's nameless variables. And all the components have their own similar file. You can go in there and change nameless variables. Okay, so now we're gonna submit this thing to, in this case, to a batch queue. And down here, you know, you can monitor, in this case, the job was submitted to this machine, but it hasn't started running yet. But when it does start running, what's going to happen? It's going to regenerate the nameless files, right? So if you did edit this, these guys here, it's going to pick up those changes because it's going to remake those nameless files. It's going to double check that you actually have all the input data, but it's not going to rebuild, because the idea is when you build it, you think you have what you want. You don't want anyone touching the executable. You want to stick with it. You know, if you're making source code mods and you want to rebuild, that's fine. You do it explicitly on the command line. There's not some script that's going to do it automatically and maybe you're unaware. Okay, so if your job runs successfully, you're going to end up with output, and it's going to end up in 2 places. The smallish output, ASCII text files, are going to end up back in your case directory, right? So, and the large output files, like binary history files that have 3D binary fields in it are going to go somewhere else. And that's on the next slide. But the small ASCII files that end up back in your case directory, well, there's a directory here that will contain a copy of all your nameless files. So it's kind of a paper trail of the nameless variable values that you used. Generally, your machine will have some kind of standard error and standard out files that show up. That's kind of a machine-dependent thing. Log files. So all the models individually create what we call log files. It's the standard out from the model. Stuff like I'm at day 1, I'm at day 2, I'm at day 3, maybe some global diagnostics, some kind of smallish data that's written to standard out and is ASCII text. And then there's some other files or some timing information. If you really get into production mode, you'll want to look at that, and it'll tell you how fast is your model running, and other information that can help you make it run faster, potentially.
For us, about how long does it take to run a WAACM, a bare bones WAACM simulation for like a week or 2 weeks?
Oh, we're getting 4 years per day, I don't know.
40 years.
4 years.
4 years per day.
With a lot of.
Yeah, that's 384.
300 CPUs. Oh, okay.
So, scale that.
So if you wanted to,
Down.
if you wanted to do a week-long simulation on like 64 processors, we're talking minutes.
That might take longer just to initialize it than to actually run a week. Okay, so this is the kind of stuff that'll show up back in your case directory. And then, all right, so generally the larger files. So what really happens is in that run directory, larger history files and restart files are made, and they're there. But what the scripts do is they take it out of your run directory and they put it into another directory we call a short-term archive directory. And what we're trying to do is collect together all the output that we really want to hang on to and kind of untangle it from other stuff that's hanging around your run directory. So the output data that you're really going to want to hang on to and sift through and analyze got moved over to this short-term archiving directory. Where is it? Again, you can use this environment variable, turn XML values into environment variable trick and do a listing on the short-term archive directory. After you do this once or twice, you just kind of know where it is, but you can find out this way. So if you do a listing, first of all, again, so all the outputs kind of separated out into each component has its own directory for output data. And then for each component, there's history and logs. So logs is that standard out that actually got copied back to your case directory, the ASCII files, and then this history is the large binary 3D field files. And so here we did a listing. Okay, so here's a logs directory, a couple of ASCII files, gzipped, and history. Okay, so here's a bunch of binary files, either netcdf or just, well, these would be IEEE binary files. So they've all been moved over there into this short-term archive location. Yeah, I think I'm close to wrapping up here. Okay, so what have we got? We had all this stuff before. We ran the model, and some of the output got copied over here into the short-term archive location, and the small ASCII files got copied back here into the case directory. Okay, so we got through all of this, and then the last step here would be continuing this run. So, okay, again, so before you continue, you want to do an initial run. You want to do a short initial run. You want to look around and see what happened and try to convince yourself that it's doing the right thing. And if that looks good, then let's continue. It's not going to be cold start anymore. It's going to pick up the restart files from your 5-day run. It's going to start from day 5 and continue. Or if your initial run was a year long, it's going to pick up the simulation from end of the first year and continue. So what you got to do is you got to tell the scripts, I don't want to redo an initial run. I want to continue. So you need to change this value in this env run file. Some other things you might want to do are, there's this stop option. This is a thing that says I'm running for 5 days or 5 years. So you might want to change that and start doing longer runs. What else can you do? There's an auto resubmit feature. So hypothetically, you could say, I want to do a 1-year run, and you could say, and I want it to resubmit 9 times, right? So you'll do a 1-year run, the job will end, it'll resubmit itself, it'll run again. It'll resubmit itself 9 times. You'll end up with 9 years of simulation that took place in 10 different runs, but you only submitted it once. So now we're going into production mode when you start doing that. You want to crank out a lot of years of simulation.
And it won't give you the same answer over and over and over again? This is
No,
like
it won't, because if it's a
continuation you're talking about?
Yeah, because
Oh, I see.
because you're saying I don't want to start
I see.
back at the beginning. I want to continue. And actually, if you resubmit, it'll automatically change it to a continue run. It's saying if you want to submit 9 times, I'm assuming you want to continue, not just rerun the same simulation.
And it does the submission, like the V-sub command by itself?
Yes.
Okay.
The last thing the job does is it resubmits itself.
Yep.
And if anything goes wrong, it'll just stop.
Yeah.
And then finally, you can turn on this other option. So I talked about short-term archiving, where it collected the important output data into this short-term archive location. Oftentimes, you'll want to turn on this long-term archiving, and it'll take, if you did 9 years of simulation, it all starts collecting in this short-term archive location. There's another script that can take all of that and put it into a really permanent location. This is common at supercomputer sites, some kind of device with permanent storage, and that's what we call long-term.
What does that DLLMS, what does that stand for?
It stands for something, like all Unix commands stand for something. D out is data out, the L is for long-term, and the MS is, well, at NCAR, the long-term archive device is called the mass store. So it's something you would have never guessed, but it actually means something. Right, okay, so I just mentioned that. Why do you want to do that? At NCAR, the only really permanent location is the mass store. The short-term archive location, while it's handy for collecting your output data all in one place and separating it out from things you don't really want, it's not actually a permanent place. The operating system will come and scrub that data for you. You got to get it out of there into a permanent location. That's the long-term archiving. Okay, so now we have the whole picture. We had all of it before, except now long-term archiving may migrate this data elsewhere. And we got through the whole process. So this page is, you can get more information. All right, here's our release homepage. There's this first guide is similar to what I just did, kind of running the overall system, but there's user's guide for all the different components. There's a bulletin board where the community can ask questions to the community. I did something went wrong. Does anyone know what's going on? And maybe someone will answer. The group I'm in, the engineering group, sometimes chimes in with answers, but not always. But it's sort of a community dialogue there about problems. Release notes. So we make a release. If we find out in a week or a month or a year that there's some bug or some issue with it, we'll put it on the web, and you might want to check that from time to time to see if there's anything you should know about. For our scientifically validated comp sets and resolutions, we did control runs. And we generated a bunch of data, and we made it all available, and it's available here. So for a variety of science runs that we did, you can check out the data there. We do have a help email. You can email us, and we'll answer your question as resources are available. We're not going to guarantee that we're going to answer right away, but you can try. I think you should look at the documentation. You should ask on the bulletin board, but certainly you can also email us directly.
I just want to point out that all the links for trying today won't be live until 11 o'clock tomorrow morning.
Yeah, so we're releasing code tomorrow.
You won't be able to access them.
So after 11 o'clock tomorrow morning, though, if we have accounts on Bluefire, we could go and we could just go and try and run this and play with it. And
Yeah, absolutely. Bluefire, it should be no problem. You should be able to run this thing in 5 command lines or 6. And I mean, we test this thing all the time. Bluefire, I know it works.
So I have 2 questions. The first is there like a test case where when we download the code, we do everything that you said, we run it, we produce a plot, and then we compare it to some plot that you've given us to say, aha, I got the right answer?
Yes, sort of. So what you get out of the box is, like, all of our control runs are available as out-of-the-box simulations. You can rerun those, and all of our output data is being migrated to this Earth system grid. We also have, if you go to our website, there's a page that has diagnostic plots of certain things that characterize the baseline simulation. So there's control runs you can compare to. There's plots that you can actually get the output data. But it's kind of a scientific question that maybe I'll defer to these guys. Like, if you have a run and it's not identical, bit for bit identical,
What does it mean?
Does it have the same climate? It's
Right.
kind of gets,
And then you didn't talk at all about visualization. Are there IDL codes out there for visualizing?
On the website, there's a link to some post-processing tools for all the components.
But for WAACM, we have a homegrown widget interface that you can get from the ACD website, and it allows you to look at the WAACM, all the way up to maps and everything. So
And there's obviously links on these web pages to
there
that.
is on the WAACM webpage.
I think that there's 2 things roughly we do to help visualize and post-processing. One is we put our output data in this netcdf format. The idea being there's a lot of tools that already recognize that format. And we do make the tools that we use in-house to analyze output available on the web. A lot of them I don't use personally, so I'm not sure how fancy they are. But we use them in-house, and you can have them. And so this presentation also will be on the web. There's actually some more slides after this that I don't have time to get into. But if you grab this presentation from the web, it's there. And so it gets into these issues somewhat. But really the best place to go is, go to the release homepage and look at the user's guides there. And that's it.